Chapter 2, Lesson 1 of Pre-Calculus, we're going to look at linear quadratic functions and modeling. Now, we've done these in years past. You've done linear equations in both algebra. Whoa, dropped my pen. We've done linear equations in algebra and advanced algebra and a little bit in geometry even. Quadratics you do a little bit in algebra, a lot more in advanced algebra. So these are familiar functions to us. We're just going to look at them again, maybe look at them in a little bit different way, or a little bit deeper way, and then we want to use these functions then to model phenomena or data in the world that we see around us. So we'll take a look at polynomial functions first, then we'll look at linear functions and graphing those and how to do regressions, and then we will look at quadratic functions and graphs as well. Polynomial functions, the definition or a definition is that they are defined and continuous on all real numbers. So defined means there are no restrictions on their domain, and continuous means you can draw it without picking up your writing device. So there are no restrictions in the domain, no restrictions in the domain in the range, excuse me. So we're looking at all real numbers. So anything that would create, or any function that creates a restriction in the domain, is not a polynomial function. The degree of a polynomial function is the number of the highest exponent. So you look for the highest exponent in the expression. That will be the degree of the function. The leading coefficient then is the coefficient of that term that has the highest exponent. So again, you'll want to look in the expression, find the term with the highest exponent. The exponent itself is the degree. The number that's in front of that term is the coefficient. Now, 95% of the time, this will be the first term in the expression, because 95% of the time they give you the expression in standard form. However, if it's not in standard form, then that first term is not necessarily the leading term, or that first term does not give us the degree of the function. So standard form, very important. Standard form is when the expression is given so that the exponents go in decreasing order. So the highest exponent is first, then the next highest, and then the next highest, going from left to right. That is standard form. And as I said, 95% of the time we will give you the expression in standard form. And the problem with that is students always then think that the first term gives you the degree and gives you the coefficient. However, that's not the case. That's only the case if it's in standard form. In that other 5% of the time, we mix up the terms. We don't put the highest one first. The highest one is second or third, or maybe even it's the last one. And that is to test and see if you are understanding the fact that it's the highest exponent, not the first term. So make sure when you come to a problem, a polynomial problem, that a nice little habit to get into, something that I do, is I always check to see that it's in standard form first. If it's not, I put it in standard form, and then I start working on the problem. Because then when I'm looking for the degree, I know it's the first term. When I'm looking for the leading coefficient, I know it's the first one. And that way I make sure I don't make that error of thinking that it's always the first, because that's not the mathematical concept. It's not always first. It's the highest exponent wherever it is. So make sure you take a note and maybe practice putting it in standard form first before you start then answering the questions. Now, polynomial functions cannot have any negative exponents in them, because if you remember, if we have x to the negative 2, let's say, if we have x to the negative 2, that's in black, I'm not sure you can read that. Let me rewrite that and get some white here. If I have x to the negative 2, that's a negative exponent. Well, how do I simplify that or use that? I move it to the denominator and it becomes positive, but now what happens? I now have a variable in the denominator, and variables in the denominator create restrictions on the domain. But we started off by saying here at the top, it's defined and continuous on all real numbers. So there shouldn't be any restrictions. So a negative exponent creates a restriction. That's why polynomial functions do not have negative exponent. Another thing that polynomial functions do not have is they don't have fractional exponents. They can only have integers for exponents. And again, fractional exponent creates square roots. And square roots, you remember, have restrictions on their domain. But we started off by saying polynomial functions, I don't know if you got that. Polynomial functions are defined on all real numbers. If you have a square root, well, the negative numbers aren't used. So again, fractional exponents, if a expression has fractional exponents, then it's not a polynomial function either. And constants. Constants are polynomial functions with a degree 0. Constant, you remember, is just a number. So if I have the number 5, that is a polynomial function with a degree 0, because I could put x to the 0 power right here. But what is x to the 0 power? That simplifies to 1. But if I write it like this, then the degree is the highest exponent. The highest exponent degree, lunch is over. Highest exponent degree is 0, so this would be a 0-degree polynomial. And that's an interesting one to look at, and we'll talk about it more when we get to linear equations, because there's an equation that we've been saying is a line all along, but technically by definition it's not a linear equation, it's actually a polynomial function, but we'll talk about that when we get there. So in mathematical terminology, if you're reading your textbook, this is what a description of polynomial function. N is a non-negative integer, so n, you'll notice, is the exponent up here, and we talked about the exponent not being negative, and it's an integer, so it's not a fraction, so that's what we talked about. The degree is the n here that's in the leading position. It's the highest n, and then the leading coefficient is just this number that's in front of that. So you must be able to put the polynomial in this form for it to be a polynomial. So again, you can't have any roots or negative exponents. Okay, so let's do a few examples of what you'll run into in your book, or examples that you'll have to do in your book. So determine if the expression is a polynomial function, and then if it is, give the degree and the leading coefficient, and if it's not, then just explain why. So is this a polynomial function? Well, I notice it has a negative exponent, so no, because it has a negative exponent. All right, how about this one? It's in standard form. It is a polynomial function. The degree is the highest exponent, which is a 5, and the leading coefficient is the number that's in front, so it would be a 2. So it's a 5th degree with a coefficient of 2. Is this? Now this is not standard form, so you'll have to think about putting it in standard form. So it is a polynomial function because no square roots and no negative exponents, so this would be a 2nd degree polynomial with a leading coefficient of -5. So I'm going to pull these last ones through pretty quickly, and you can check and see if you got it right as I go along. That's a constant, 0 degree, leading coefficient is 13. Okay, what about this one? Now this one is not, because it has a cube root. So again, roots are not polynomial functions. So no, it's a cube root. Alright, so those are polynomial functions, and that will wrap up this first video. We'll take a look at linear functions in the next video.